Hello everyone, welcome back to Tux Riders. In this video we want to have a look at general aspects of numerical solution of PDEs, partial differential equations, which consists of like a first order convection equation as well as a diffusion equation, and we will talk a bit about the stability conditions and this sort of stuff. So let's go for it. Okay, so let's start with discretizing equations. In previous video we talked about that, but that was for, an ordinary differential equation. For partial differential equations, we deal with two variables, two or more variables that the main state function, the main function of interest depends on. That can be like the time, space, and different coordinates, different dimension of the space. That's why I said more than two. But in the previous video for the initial value problem, what you saw was only dependent on time. But in this case, let me open the first notebook. As you can see, the title of the notebook is space and time, which means that now we have a sort of equation that depends not only on time, but also on space. So this function u is dependent on both time and space. As a result, the techniques that we saw in previous video are not really sufficient for this. We need to deal with more advanced techniques. The technique that we want to start with, which is actually the technique that we started from the discussion on from previous video, is finite difference method. In finite difference, there are a couple of techniques, there are a couple of technical discussion behind, for example, the term characteristic curve, and also a couple of more mathematical terms. I don't want to go to the details of the mathematics. This is really from applied point of view. So when we want to apply the finite difference, as I discussed in the previous video, we discretize the space or time into different points. So let's say that, for example, this is the coordinates, this is the coordinate system along the x. We divided it into different points. And then we say that, yeah, for example, this is the point 0, this is 1, 2, till the point n, actually. But for partial differential equations, we have another variable. So let's plot it like here, that is t. And then we should divide t also into discrete space, into definite number of points, let's say. So it can be like here, 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 and on t we have also the definition. And then as a result, as a combination of these two axes, we have more. Let me see if I can plot it with yellow. No, it's not visible. So like this, you see that they have different points, and each point is correlated to one x and one t. So we want to actually study the state of the system like u at each point x over time. This is how this is actually the difference between what we want to discuss here and what we discussed in previous video. So as you can see here, this is what I was talking about. So we have different x coordinates which are denoted with this subscript I, and then superscript n for time. So what we write as, for example, UNI means the state or the value of u at point x at time, at point I at time n. So this is a kind of notation that we use a lot during this course for really finite difference and also for finite element. So let's go on, and you can see here it says that, for example, when we want to say that the current time step, you remember from the previous video that what that means. We iterate through both axes, through the time and also through the space, and at each point the un means the current time step, and n plus 1 means the next time step, and n minus 1 previous time step. Same for this. Actually, the coordinate system on a spatial derivative, spatial, let's say, coordinates. So it means that current point, the next point, and the previous point. Okay, so let's go on, and as you can see here, it says that yeah, xi means the I of delta x. So for what we actually divided the space, it was for example here and here. For the points on the x coordinate, we say that the difference is each step is delta x, and for t, actually each step is delta t. So this is the time step, and sometimes this is called mesh size also, because this is actually, we usually say that we discretize the space, and for time we use the term time step, and this is the mesh size or grid size. Okay, let's go on. And for discretizing the equation, that's pretty simple, but it's also very cool that we see how this formulation is derived. That actually the derivative of u in respect to x is equals this one. This is actually the numerical differentiation, if you know it. So where does this come from? This is a kind of demonstration, a kind of graphical scheme that shows how we can compute the derivative of a function at any point of desire. So let's say that this is actually the coordinate system that we have, and this is a function that we want to evaluate the derivative here. So this is actually the point x or xi. It doesn't matter, that we want to evaluate the derivative here. So the derivative can be draw the exact derivative, that is the slope of the function, slope that we can draw at that point. So this is the exact derivative. You can see it is here in the black curve. The exact derivative is this one. But if we don't have the analytical solution of the function, let's say that this is f and this is x, so this is f of x. If we don't have the exact or analytical solution of this f of x, then we cannot derive the differentiation, and we don't know what is the slope actually is here. But if we go a bit further, or a bit back behind, and choose another point here or here, and then we connect these two, let's say, 2 points, and we can easily compute this slope because we have the value of x at these 2 points, or here it means that we can compute the value of the slope, which is actually, the formulation of the slope. And this is the way that we can compute the numerical slope of the function of x at xi. This is called forward difference, and this one is the backward difference, or let's say forward formulation of differentiation and a backward. And there is also a central one that we can say that yeah, we connect these 2 points together, and as you can see, this one has a more accurate representation of what, and it is a closer value to the real slope. And this is how it means how you can interpret this very nice graph here, that it shows you how the exact slope at each point is correlated to forward and backward and central difference or central differentiation. And using this technique, we can easily come back and compute the derivative of u at any point, because we have the value of u, we have the value of f, and using this we can compute the derivative at any point x. So quite cool. And as you can see, this is what I said here, that this is the forward difference or the backward difference and the central difference. For the central difference, what is important to point out is this value is actually 2 delta x, because we have 2 delta x of the difference of these 2 points. But as you saw, the central difference has a more accurate calculation of the slope at the point. So for the equation that we had here, which was let's say this one. So let me write it here. That this is the partial derivative of u in respect to t plus c. the derivative of u to x is 0, and this is the velocity of the convection. For this one, the formulation can be, let me also remove this one. The formulation can be using this central difference and backward difference, forward difference, can be written as simple as that. And if you remember the formulation, the type of notation that we had beforehand for this kind of, for discrete space, you can see that it says for the backward difference, this is a forward difference in time actually, and it's also called Euler formulation. For the forward difference in time, just imagine that this axis is time. For the forward difference, we can rewrite this term to this term. And then you can see that for the normal derivative, for the partial derivative of u to x, again, this time using backward difference is this one. So this is forward difference in time, as you can see, next time step minus current time step, next minus current, plus the backward difference in space. So the current time step, current coordinates I minus the previous one. So this is actually the backward difference. And using this formulation, we can easily compute by writing a simple program. As you can see, we can also, let's say, kind of rearrange this formula into the one that now we want to solve each time, each coordinate, the value of u at each coordinate for the next time step, assuming that we know the value of it in previous time step. And this can be drawn using a concept called stencil, here demonstrated here actually, that each value of u at the coordinate I at the time step n plus 1 depends on the previous time step, because it is a forward difference in time, and also, the values of I and also the value of u at the previous coordinate point, let's say, in x. So this is the concept of numerical computing. And if we want to iterate through this equation, simply we iterate through this and we compute the value of u for any point in time and in space. And iteratively we obtain this solution. Let's do that for a very simple, let's say, equation, for a very simple problem setup. Let me remove this. Yeah. And the problem that we want to solve is actually sort of, this is a discrete or kind of signal that is 2, the value between 0.5 and 1, this is 2, and in the rest space it is 1 actually. And we want to move it through time to the right by a velocity. You know that it's c in the equation that I showed you is the velocity. And for doing this, we discretize the space into 41 points, and this is the number of time steps that we want to solve. And within a space, I don't want to go to the details of the implementation. Within a space, we discretize the time with the space, and then with the var function of numpy, please refer to the numpy video. If you don't know what var is or what ones is actually, please refer to the video. We initialize this, let's say, array. And by doing that, it would be something like this. So you can see that in a space that is not between 0.5 and 1, it is 1. And inside this, that is 2, which is these values. So this is the initial value of u. So just imagine what we have here is something like this, that this is the u, this is x, and we want to see what happens to this wave, to this kind of signal over time, that this is actually 1, this is 2, and then we want to see what happens to this. So let's see. Let's do that using numerical computing. So this is the initial condition as I draw here. And then using this iterative formula, we want to see how it goes on. So with this very simple Python, let's say inner loops or nested loops, this is the loop on time and this is the loop on space. We go on, we compute the value of ui is actually the value of, let's say, we have two variables here. One is un, which keeps the previous time step, the solution in previous time step, and u is the value of the current time step. So you can see how this backward, this is actually the backward difference in space, and this is the forward difference in time. And we compute the value of u, and then we plot it, and you see after 25 time steps, it is moving to the right. And this is the beauty of numerical computing, as you can see how it moves. And then, yeah, that's it. And then there is another notation that is important to mention here. And the notation is the big O notation. This notation. The big O notation, it means that, for example, for writing the formula that we had for the numerical differentiation, we omitted the terms or approximation, because you saw that for numerical differentiation, it is sort of approximation actually to the exact derivative. We omitted the terms that are higher than the order of 1 here. So when someone says that this is, for example, the order of 2, big O notation with the order of 2, it means that it's a second order of accuracy, because we have included the second order of delta x into a formulation, but omitted the bigger values. So this is a kind of notation that we use. So for solution that we had, that you saw actually, we had the second order, the first order of accuracy for both time and space. And when you go to the literature, people talking about numerical computing, they usually refer to this accuracy like they say that we have the first order of time and a second order of space, or even high orders for increasing the accuracy. Okay, so let's go on. And this is also nice because you saw that's how simple it is to compute the numerical solution of the partial differential equation. It can be also a nonlinear convection like this one, that instead of the velocity c, you add u, which means that every point with higher value of u has a more velocity, let's say. This is what this equation implies. So for doing that, it is quite simple. Instead of c, we insert u into the solution, into the equation, and then we can compute the finite difference solution of that. You can see here, it's easy, and that this is the initial condition, let's say. As I described in the previous video, this is the initial condition. And then for implementing it, this is how they have vectorized the solution. So yeah, this can run faster, especially if it is with NumPy. But I don't want to go to the details of this. But this is a sort of way that you can omit the two sides, the two ends of the spectrum using these kind of Python notations. But this is not something that we want to deal with. And this is the numerical solution of the problem when we employ just the nonlinearity, which means that points with higher value of u, they have more speed or more velocity, and the speed of the speed at which the equation is convected is related to the solution of the equation. Actually, this is how nonlinearity occurs in this equation. So yeah, this is quite nice, very nice actually, I can say. Okay, that was what I wanted to discuss on very general aspects of numerical solution of partial differential equations. And you saw how we could employ those techniques, the finite difference, backward difference, forward difference, and these kind of concepts to solve a simple, let's say, one-dimensional linear convection and also nonlinear convection equation. And then in the next videos, I will describe why this stability matters a lot, and also we will try to discretize the second order of accuracy for a space and in order to solve the diffusion equation. Yeah, have fun and see you in next videos. Bye.